Hello everybody. We are going to discuss on nonlinear and fiber optics today. Here in this part, in this is the first part of our discussion. There will be several part in this topic, nonlinear and fiber optics. Uh, Here, this is the content of our of this talk. We'll first give a brief introduction about what is nonlinear optics and what are the introduction, what are the interactions, linear as well as nonlinear interaction of light with material. Then a little bit theoretical background from where this nonlinear optics came into fore. Then this Franken's experiment, which is the first experiment that resulted the observation of nonlinear optics in this domain. Then we'll be discussing on a little bit about the nonlinear optical processes, second harmonic generation, third harmonic generation, etc. And the consequence of third harmonic generation will be given at the last in this topic, in this part. So we are going step by step. First is the introduction. In this introduction, we are going to discuss what is nonlinear optics. It is basically the study of phenomena that occurs as a consequence of modification of optical properties of a material by presence of intense light. Various terminologies have been coined here. First is the consequence of modification of optical properties of material. Optical properties of material can be modified uh, by uh, by the light, but when it was ordinary light whose intensity was very low before the advent of laser, it was unable to modify the properties of light to a greater extent. So we had only few properties of matter, optical properties we able to see. But later on, when intense light came into exist, means when laser have been invented, then we able to know that no material property can be highly manipulated by introducing this intense light. So this is a small animation that we are going to that we are showing here. This is 1900. I'm just showing from 1900 to 2000. So 100 years development. um, Basically optics was in the forefront of progress in physics from the very beginning, when this modern science have been evolved. From that point of time, we were knowing about the reflection, refraction, interference. We encountered these things at each step of our lifestyle. So we are knowing about those reflection and refraction, and we use that in higher extent. So because of that, we can say that optics was in the forefront of physics, forefront of progress in physics. What was the reason? There were two reasons. First one is large availability of analytical solutions. It means that when we interacted light with material, then we able to see those four phenomena like reflection, refraction, interference, diffraction. So those can be analytically solved, and there was large analytical solution which were available at the time, and we whatever problem arises at that in this era till 1930, we able to solve it with this by these analytical models. And we have the results, we have the outputs. Second point was superposition phenomena. Superposition phenomena was a very great tool to which is quite successful to explore the complete knowledge of a system. When we launch light into the material, then light will be interacting with each other, then superposition will be happening. Superposition stands for combination of different light with their frequency, and it produces the damp frequencies and intense frequency. It is this amplifies sometimes, then de-amplify, etc. And this phenomena can give rise to the information about the system. So because of these two reasons, we able to encounter a lot of things in the optics. So that in turn gives rise to a lot of phenomena and lot of understanding about the material as well as the system. So but from 1930 to 1960 there was a pause in optics. There were two reasons of this pause. First is the fundamental problems have been solved, means whatever the problem we had till that time, it was those have been already solved. So because we had the two great tools, one is analytical solutions are there and superposition principles were there. So whatever problem in optics we found, that have been encountered immediately, and that is solved. Number two is investigation on atomic absorption is no more interesting. Atom absorbs light definitely. So uh, we had we had light sources like our sodium lamp, our mercury lamp, etc. Those were preliminary sources of light before the advent of laser, and we use those lights in a rigorous fashion. And the problem with those lights were that though they able to interact with atoms or molecules, but they unable to invent, unable to go inside the atomic radius. That is why we have a very limited phenomena, and because of that, since it was a limited phenomena was encountered, so one time came that when uh, problems were finished, so there was no such fundamental problems to tackle further. So regularly, gradually, the importance of light, importance of optics, or the interest in optics have been decayed. Then, so that we call as pause in optics. So optics was no more interesting field. So till 1960, here one more thing we need to mention that the theory of laser came in 1917 by it was given by Einstein, but unfortunately from 1917 to 1960 there was no physical laser source or no physical working laser that can be um, that can be useful for our research purposes or daily purposes. So first operational laser was invented by Theodore Maiman in 1960. The moment when this special kind of light sources have been developed, it has been it come with it the laser source came with lots of properties, like it is a coherent source, it is highly monochromatic, highly unidirectional. So all these things, all these properties of this new light source gives rise to intensify of this light, new light. So because of that, now let me discuss this part. Here you see, before laser what was happening. Light intensity has no effect on the properties of matter. intensity, since light intensity was very small, so it was unable to affect the properties of a medium. So you can see here that the electric field strength of any conventional light source, yeah, the electric field strength of conventional light source was 10 to the power 5 volt per meter. So that is only able to give only able to interact with the atom or the molecules. It able to change the molecular structure or able to excite the molecular atom, but it unable to go inside the atom, because the electric field strength required in the uh, um, interatomic yeah, interatomic domain is 10 to the power 9 to 10 to the power 12 volt per meter, which was not even not enough produced by these conventional laser sources like we use in our early days, in our before advent of laser. And here we see that when laser have been invented, that these lasers are of 10 to the power 12 volt per meter, so definitely it can encounter the interatomic domain also. So it immediately able to change the properties of light, because we are now by introducing inducing this laser, we able to change this material system, and that will be that come out as a best result, uh, means changing the properties of the material. So here we can see what was going on in linear and nonlinear optics, in linear and nonlinear interaction. In linear, before this advent of lasers, interaction of light with matter, we can see that, say for example, these are the energy levels of a medium. This is, let's say, a molecule, and where we are giving an input of, this is a red light. We are using conventional light whose frequency or wavelength is in the red domain, it's in the red color, and we are getting the emitted wave is also of red color. Here we can see the polarization is a linear relation with the electric field. So here we see that this light is only able to excite to the first excited level, and this is the input, definitely the input of input photon energy, and definitely when it will be emitted, the emitted light the emitted light photon energy is of this the same energy. So so when we launch red light, and it though it excite, but excite only up to first excited state and comes down immediately, the photon comes down to the ground state. So there is no new color we can see. So there is no interesting point we can find from this linear interaction. Now, after the advent of lasers, what we can see here is that due to the interaction of light with matter in the nonlinear regime, the polarization is now of this relation. Here we can see that P is the polarization, epsilon naught vacuum permittivity, chi 1, chi 2, chi 3, etc. are the susceptibilities. Yeah. And E is the electric field strength or the amplitude. So here chi second order, chi third order are introduced, because now initially it was not introduced because the intensity of light was very small. It was not even seen. So here now when laser are there, intensity of lasers are very high, because of which we are able to see the effect of chi 2, effect of chi 3, means these are the nonlinear susceptibilities. So as a result, we can what we encountered, this is the same molecule. Now we are using a laser source of red light, And we see what is happening here. This is the ground state, then first excited, second excited. Now the atom, the atom able to change, able to take up the photon and goes up to first excited state, and at the same time it able to from the first excited state it able to take another photon of energy, same energy, and it goes up to next excited state. And when it is coming down, when the atom is releasing its energy, these energies are released at a combination of these two energies. So red plus red gives rise to another frequency which is of the order of blue. So we can see, if even if we are launching a red light, we are seeing a new color from here. Definitely red will be there, but a new color in addition to this red color will be also seen. This gives rise to a new phenomena that, oh, not monochromatic light. When we launch monochromatic light and it is intense light, when we launch into a molecule, then it can produce a new light, new color, and that probably changing this the um, what is called the frequency, input frequency. And how it is changing the frequency? Because of the intensity. Since intensity is higher, and because of which two photons are getting absorbed, and in the output we are getting a new color. So after the advent of laser, this new phenomena have been observed, which was unable to see when the laser was not discovered, and we were using the what is called conventional light sources. So because of advent of laser, the optical industry have seen new phenomena, and which have been made this pause in optics again activated. So now from here, from 1960, after the 1960, the optics research was in track again, and now it is the optics in the again it is in the forefront, and it is changing the world in the mass scale because of this nonlinear introduction of this nonlinear optics. So this is a little bit about the theoretical background. Here what is there, this we are just giving a and what is called, this is a animation. This is an atom. We know that atoms are composed of positive charge and negative charge. Positive charge at the center in the nucleus, and the negatively charged electrons are revolving around the nucleus. And if we consider that the inner part is the central part is positive, then the outer part, the whole other part will be filled with negatively charged particles, and they will be producing negative charge as a whole. Both this positive and negative charges will be balancing each other, and there will be no charge of the system. And no, there will be no this one uh, no dipole moment to produce when electric field is not introduced. Now, if a beam of intense light is launched into this medium, then you can see the electrons and nuclei, and they, they, they get separated, because now you see when an electric field here electric field was zero, and here electric field is not zero. Definitely when an electric field is introduced into this medium, the medium will be this, or the atom will be change its shape, producing a negatively charged particle to take a side, and positive charge to take in the other side, producing a dipole moments. It forms dipoles. So electromagnetic field interacts with the dipoles, causing them to oscillate. Now that will be, since it is an electromagnetic field, that will be producing this material which will be start oscillating now. Positive now this side positive, next side will be this positive charge. Charge will be here, and the negative charge will be other in the other way. So there will be an oscillation to take place. With this increase of intensity, polarization ceases to be linear. Here in this situation, the polarization will not be not be linear, that will be non-linear. So oscillation result in the radiation of different frequencies. These oscillations basically, when there will be oscillation, that there will be production of dipole moment, and that dipole moment will be keep on changing, and this producing these different frequencies in the output. And because of what we able to see from we use the red light, and we found a blue light. The red light will be there also again. So this was the theoretical basic theoretical background, which was given by Bohlen-Person in 1962. And in 1981, Nobel Prize for Physics have been recognized for this work, developing the driving principle behind nonlinear optics for laser spectroscopy. So in 1981, the Nobel Prize was given in this domain, and since it is the primary requirement for the production of new frequencies, and this uh, phenomena can give rise to a lot of information about a molecular system. So definitely that will be very interesting, and people can take up this phenomena, and uh, give a new domain, give a new test, give a breakthrough and new domain of research, domain of study, which can give the society new devices, new optical devices. And definitely there are a lot of optical devices now we have been seen, which is based on this nonlinear optics. And that the world is now growing with this there are these optical devices, and because that are very suitable for our, not only now in laser industry, and but also the civil industries, as well as the medical sector. Lots of instruments which are based on nonlinear optics are implemented, developed and implemented. Now we are going to discuss on this Frankenstein experiment. Yeah. Now coming to this Franken experiment, this is the first experiment that results to nonlinear optics. This was done in 1961, 1 year later than the discovery of laser. This was the first observed by Franken and co-workers, that when a light was produced, was launched into a nonlinear medium, quartz crystal, then it produces the second harmonic generation. Means what? If we send a frequency omega, then we can get another frequency of twice omega. So this was done in University of Michigan. What this experiment says, that they use a ruby laser. Ruby laser was the first laser, solid state laser, that was discovered, and it was discovered by this team Eman. Definitely, that ruby laser was used here. Ruby laser of frequency omega 1, which in turn give rise to a wavelength 694.3 nanometer, was launched, and there was a red filter was used. From ruby laser, many other lasers also, other light can also be produced. To stop those other lights, we use a red filter, such that only red color of this wavelength can pass through. Then it was launched to a nonlinear crystal. In that nonlinear crystal, we able to see what is going on inside. Uh, Here, we have seen that omega 1 frequency was passed through it without any without any loss, because the crystal was very small. So there was no loss in this omega 1. And fortunately we, or unfortunately, we able to see another very small light, means small intense light of omega 2. Then this omega 2 was fall in the UV range, so we use the UV filter such that only this light can be passed through, and it blocks the red light. Okay, so it has been seen that omega 2 that evolved is equivalent to twice of this omega 1. Or if we talk about talk in terms of wavelength, then we see that 694 nanometer wavelength is found to be at half wavelength, which is found in which is produced by this nonlinear crystal. Then in the photocell it has been captured, because we cannot see the UV light, only a photocell can detect it, and it has been detected as half of the wavelength, means double of the frequency. So the laser launched at 694.3 nanometer, and the average power of the UV laser was 10 kilowatt. So an additional UV light was obtained at wavelength 347.2 nanometer, which is just double the launching frequency. That is, it is producing second harmonic. So it has generated second harmonic. So, but the average power that UV light was obtained at 1 milliwatt only. But and this was the you can see that we used a wave of red laser, and in the output we are getting a blue light. From a red light we are getting a blue light. From 694 nanometer wavelength we are getting a 347.2 nanometer wavelength. That was very interesting. So this similar observation can be also seen in pre-laser era in the Raman effect. In 1928, Raman have discovered this effect, that when you are launching light into monochromatic light into transparent medium, then it produces Stokes and anti-Stokes lights. Sometimes it what is called quite most interesting, because it produces uh, frequency half of frequency or double of frequency. This way we also have seen that Raman effect was also discovered. But when this laser have been produced, laser have been invented, then this Raman effect are intensely very what is called effectively understood, effectively observed. So with that, so we are finishing today's lecture, and we'll be discussing the rest of the part in the next session, which will be produced very soon. So up to here, what we have discussed, we discussed about what is nonlinear optics, and what is the background of it, and what is the first experiment of this nonlinear optics that lead us to the observance of the first experimental result of the nonlinear optics, where we have observed the second harmonic generation. Okay, so with this I am finishing the first lecture. I will be meeting you all in the second lecture. Thank you.